Hello everybody, welcome to our video solution to problem 3 from Superquiz 1. In this problem we have a little story about a wonderful woman I know, and this is absolutely a true story. She's currently receiving treatment for a very severe ailment, and when they intravenously administer this treatment, the body immediately starts removing and converting some of the medicine at a rate which is proportional to the concentration in the bloodstream. Okay, so here C, you can see down here, C is going to denote the concentration in the bloodstream. And when we say things like a rate proportional, right? So this proportional means that you're going to have some constant times that, right? And so K here is going to be some experimentally determined constant. And how do we know it's getting removed? Well, you see there's this minus sign. Okay. So I here is going to denote the constant rate at which the drug is being added to the bloodstream. So if we want to know the rate of change of the concentration, right? So dC dt, right? That's the rate of change of C with respect to time. I is how much is coming in, and then you're subtracting, right, an amount which is proportional to the concentration in the bloodstream. Okay, so this is a differential equation which models C, and we'd actually like to write down a formula for C. And that's actually what question A is saying. Use the method of separation to find a general solution to this differential equation. Okay, so let's take a little peek. So we have, I'll copy this differential equation down. We have dC dt is equal to this constant I minus this constant K times the amount of concentration at time t. So the method of separation says we want to put all of the C's on one side and the T's on the other side. So what I'm going to do is multiply both sides by dt. Okay, that'll get this dt away from the dc. And I'm going to divide both sides, well, by this entire expression, I minus kc. Okay, that'll keep all the C's on the other side. So when I do that, I'll get dc divided by I minus kc is equal to dt. Okay, so I'm really just doing a little square dance step here, right? We're just swapping the places for dt and I minus kc. Okay, next step, right? We've now separated. Now we're going to integrate. So I'm going to apply an antiderivative to both sides. And of course, when I do, I have to be very, very careful because, see, our definition, right, when we write this symbol is we're taking an antiderivative. But we know that antiderivatives, right, are all the same up to a constant. So when I take an antiderivative of both sides of an equation, I really can't be sure I'm taking the same antiderivative, right? So I have to only say this is true up to some constant. And notice I don't use the letter C here because we've already used that as our variable name. And I'm going to say for some constant D. Okay. All right. Well, now we got to do a little antiderivative. And this isn't so bad. It looks complicated because you got all these different letters, but I and K are constants, right? This would be the same thing if we'd written down something like dx over 3 minus 5x. Okay. Or maybe even you prefer to write this as negative 5x plus 3, and you go, hey, look, this is very similar to what we did in video 1, right? When you look at something like 1 over x, right? An antiderivative of this is ln of the absolute value of x. Okay, so all we have to do here is guess that it's going to be basically the same thing. All right, this would be, we're going to guess ln of the absolute value of 3 minus 5x. But if we checked it by taking a derivative, the chain rule would yield an extra negative 5. So we have to compensate by dividing by negative 5. Okay, so the same thing is going to happen here. Okay, I get natural log absolute value, I minus kc. But if I took a derivative, I would get an extra factor of negative k. So I'm going to divide by negative k here. And on the other side, well, that's the easy side, right? If you antidifferentiate dt, you just get a t. And then we still have this plus d. Okay, well, why don't I move this negative k over to the right? That'll make life a little bit easier for us. So I have the natural log absolute value of I minus kc is equal to negative kt plus well, actually, it's going to be negative k times d. But again, this is just some constant d. It's just another constant now, right? So I'm going to keep writing d, and I'm going to say for some constant d. Okay? It doesn't have to be the same constant that was up here. Okay, well now I have a natural log. I'd like to get rid of that. So I'm going to exponentiate both sides, right? E to that power. So when I do that, the natural log is going to go away, and I'll get absolute value of I minus kc is equal to e to the negative kt plus d. Okay, now I'm going to use exponential laws to break this up. E to the negative kt times e to the d. And this e to the d is yet again a constant, right? So I'm just going to give that a generic name. Let me call this a. Now I know that a, right, would have to be positive because it's an exponential, right? A is positive here. But I have these absolute values. I'd really like to get rid of those. And all those absolute values are doing is either nothing at all, if this is a positive number, or they're putting a negative in front if this was a negative number. So what I'm going to do is just allow that positive or negative that we're getting to get absorbed by this a. So this tells me that if I drop the absolute values, I get a e to the negative kt, but now a is allowed potentially, right, to be just some real number, okay? So a, some constant, not necessarily positive anymore, okay? It could be negative. All right, well now I'm trying to solve for c. That shouldn't be so bad. I'll subtract I and then divide by negative k. So subtract I followed by dividing by negative k. So let's see, we're going to get c equals, so when I subtract I, I'll get a negative I plus a e to the negative kt, and then I divide by negative k, and I can rewrite this maybe. Let's see, that's going to be a positive, so we'll get I over k minus, well, a over k, again, it's just some constant, so I'm just going to leave it as an a, e to the negative kt. Again, a is some constant. Okay, I don't worry that there was a k put into there. Okay, and I now have an expression for c. I found a solution to this differential equation. C is going to equal, well, whatever this ratio of I to k is, minus some constant times e to the negative kt. Okay, so that's my general solution. All right, if we wanted a particular solution, we're going to need a data point. Now let's see what problem B said. They gave us a data point. It said assuming c of 0 is equal to 0. Okay, let's head back down. So if we know c of 0 is equal to 0, 0 is equal to c of 0. So when t is 0, what do we get? Well, I over k is some constant minus a times, okay, we get e to the negative k times 0. Ooh, that's e to the 0, which is 1. So I just get I over k minus a. And so if I add a to both sides, I get a equals I over k. And so my particular solution is going to be c equals I over k minus I over k e to the negative kt. Okay. And again, everything else here, right, the i's and the k's, those are constants, right, which are determined by the setup. I was how much the constant rate that they're putting stuff, the medicine in. K is some experimentally determined constant, so we don't need to solve for those at all. All right, now let's see. There was some part C. What's it say? Again, in this situation where C of 0 is 0, how much of the concentration will be left in the bloodstream in the long run? All right, i.e. as t goes to infinity. So let's see. Is there actually going to be stuff that's just going to stick around forever? So as t goes to infinity, what happens to I over k minus I over k e to the negative kt? Well, these are constants. You have this exponential, and you're raising it to, okay, negative kt. So as t is going to infinity, then okay, well this is a positive constant k. As t is going to infinity, exponent is going to negative infinity. And if you think about the graph, right, of an exponential function, right, we'll use t, say. So there's your graph of e to the t. As t goes to negative infinity, that's to the left, the exponential is going to 0, right? That's the decay direction. All right, so this actually goes to 0. Hit it with I over k, still goes to 0. So the only thing left is going to be I over k. So if we actually know this value I and this experimentally determined constant k, we'll actually know in the long run how much is going to remain in the bloodstream. All right, hopefully this is very helpful, and we'll see you again.